All right, in this podcast, we're going to talk about the idea of collision theory. Okay, so what do you need in order for a chemical reaction to actually occur? Well, you need three things. Number one, your particles must collide. Number two, they must collide with enough energy. And they must collide not only with enough energy, but also at the correct orientation. All right, so when molecules collide, this is the only way that we're going to get them to be able to break their bonds and then for rearrange to make their product. However, molecules are constantly colliding, so how come only a small percentage of them, of the collisions, actually give us a reaction? Well, the whole reason behind this is because the collisions, not only do molecules have to collide, but the collisions have to have enough energy in order for the reaction to occur. The energy needed for the reaction to occur, we call that the activation energy. And so they have to be able to overcome that activation energy when they collide. So they have to have enough energy. And then they also have to have the correct orientation. So they can't just collide any old way. They have to collide in the way that is most beneficial for them so that a reaction can occur. All right, now I already mentioned activation energy, but officially it is the minimum amount of energy that molecules must collide with in order to produce a successful collision and then therefore rearrange to form products. Sometimes you will see us abbreviate this as E sub A, so activation energy. All right, so this is what we call a reaction coordinate diagram. A reaction coordinate diagram is going to show you the total change in energy from the beginning at the reactants to the end at the products. That first big hill there, that's the activation energy. So that's the energy that's needed for the substance. They have to collide with this much energy in order to actually break bonds and rearrange. So on the graph, this right here, the hill, that is the activation energy. All right, now the difference between your reactants and products, that's the change in energy during the course of the reaction. We call that enthalpy, and it's abbreviated delta H. We'll go over that in much more detail later. Okay, now with these reaction pathways, you can have endothermic reactions or exothermic reactions. So hopefully you remember from middle school, endo, so I always think into. So these are reactions that absorb energy. And then you have exo. Exo, exit is what I like to think of. So these are reactions that release energy. Okay, so if you'll notice, they both have activation energies, right? Okay, so the difference between endothermic and exothermic, the products have a much higher energy than the reactant. So the only way this could happen is that energy had to be added into the system. It had to absorb energy. All right, now exothermic, your products have a lower energy than your reactants. Okay, so there's actually extra energy left over that the molecules don't need anymore, so they're going to release that energy. Okay, so back to collision theory. How can we make a reaction faster or slower? So in order to do this, you got to influence the things that are related to collision theory. So basically we're talking about the collisions of molecules and the energy with which they collide. So if we want to make a reaction faster, we need to make the molecules collide more, and we need to make them collide with more energy. Okay, so here's some ways that we can do that. All right, so we can change the concentration of the reactants. The concentration is just literally the amount of reactants that we have. So if we increase the number of reactant particles, then there's going to be more molecules there, and if there's more molecules, there's more likelihood that they're going to collide. Okay, the opposite is also true. If I take away reactant molecules, there's going to be fewer of them, so there's less possibility that they're going to collide. All right, temperature. Temperature is a surefire way to affect the rate. So if you increase the temperature, you make your molecules move faster. They have more kinetic energy. And kinetic energy, hopefully you remember, is the energy of movement. So they're moving faster. So they're going to collide more, number one, because they're moving faster. And they're also going to collide with a greater force or with more energy. Okay, so we're kind of increasing the collisions and the energy with which they collide when we increase the temperature. Now, if you decrease the temperature, the opposite will happen. Molecules are slower, they got less energy, so they're going to collide less often and with less force. All right, the next thing we can do is we can manipulate what's called the surface area. So if it has a lot of surface area, big surface area, it means basically it's a bunch of small particles. All the surfaces of the small particles are exposed. Okay? If there are more particles exposed, that means there's more likelihood for a collision. So that's going to increase our rate. Now, if we have less surface area, like I just have one big glob, okay, only the molecules on the outside are going to be able to react at a time. So kind of like it'll have to eat through each layer for the reaction to occur. So that's going to be slower. All right, here's kind of a visualization of that. So over here you see we have a large marble chip versus a bunch of small ones. So in the small ones, you can see that the molecules can get all in there in between, and there's more areas for them to react. Opposite holds true with the big paper, right? It's got to get on the outside pieces first before it can work itself in. I kind of think of this like a campfire, right? When you want to make a campfire, you split your wood, you get a bunch of twigs, things like that, right? You're increasing the surface area so that your fire will burn better. If you just throw the whole tree on there, okay, just throw the big trunk of the tree on there, it's not a very good fire because it's going to have to burn the outside of the wood. Only the outside of the wood's going to be available, right? So none of that inside wood is going to be helping your fire to go. All right, the next thing that can affect the rate is the pressure. So when we increase the volume, which means we make our box bigger essentially, molecules are able to move further apart. And the further apart they move, number one, the less they collide, and they're going to collide at probably a slower rate, okay? If we decrease the volume, that means makes the box smaller, we have increased the pressure because we're forcing the molecules closer together. So they're going to have to collide more. So that's going to increase our rate. I want to make note here, okay, that pressure and volume are only going to affect reactions that have gases in them, okay? So make sure you make a note of that. All right, and last but not least are catalysts. Catalysts work a different kind of way. They actually change how the reaction happens, okay? So you're still going to start with the same reactants and end with the same products, but what it changes is this middle area, okay? It changes your activation energy, so it lowers it, which means that you need less energy. They have to collide with less energy in order to make a successful reaction. So if I add a catalyst, that means automatically a higher percentage of my sample is going to collide with enough force in order to have enough energy for the reaction to go. All right, and then please note that catalyzed reactions, this is how it would appear on a reaction coordinate diagram, okay? It makes the humps. All right, so a little bit of practical application here, okay? Glow sticks, why do we snap them? Well, actually, inside of a glow stick is like a little kind of like glass thing. What it does is there's one chemical inside of it, and then there's another one on the outside of it. So when you snap it, you're allowing the two particles to react and therefore give us the glow, right? So how long does our glow stick last? Well, this all depends, right? It's variable. It depends on a couple things that we're going to talk about in just a second. Is it always the same brightness? I don't know about y'all, but when I got mine was really bright, and by the time I got home from, the roller rink or whatever, it was kind of dull. It was no longer exciting, right? I was very disappointed as a child. All right, so when we know that it keeps producing that glow, right, as we go, which means that we're continuing to get reactants turning into products, okay? So if that's continuing to happen, what that means is that there is a portion of our chemicals that are unreacted, okay? And they react later on. So why don't they just immediately react? Everybody reacts, turns into products, and everybody glows, and then we're done. Okay, the reasoning is because they don't have one of those three things. Either they're not colliding with enough energy, or they're not colliding with both enough energy and the correct orientation. Okay, so you got to have all three for a successful collision. All right, now, what do you think would happen if I took a light stick and I placed one in hot water, and then one in cold water, and then left one at room temperature? Okay, let's think about this. So if it's in hot water, the molecules move faster, right? So we would expect it to glow brighter because your reaction is increasing, okay? Now the one in cold water, I don't know about you guys, but I used to put mine in the freezer when I got home because then it would still work the next day, right? So that's because putting it in cold makes your molecules slow down, and when they slow down, they collide less, they collide with less energy, and therefore it is very likely that they will not all react, okay? All right, now we keep the one light stick at room temperature because we need that control element, right? We need something that is our control, okay? And the whole reason why particles have to hit with a certain amount of energy is to break those bonds in the reactants, okay? Must break those bonds.